Hello, this is Tracy. Welcome back, Math 135, Introduction to Statistics. We are going to go over Section 4.2, the mean or expected value. Those two phrases mean the same thing. And the standard deviation for discrete random variables. We are also going to talk about the law of large numbers. So, the mean or expected value when we are talking about a probability distribution function means the average value you would get if you conducted your experiment a bunch of times, or if you took a lot of different trials, a lot of different subjects. So you conduct your experiment, like rolling a six-sided die, a whole bunch of times, record your roll, and then find your average. Or you find data on a whole lot of subjects, like height, and you figure out the average height of all those people. We calculate the expected value for a probability distribution function the same way that we calculate the mean of a data set from a frequency table. When you used your calculator to find the mean for data presented with a frequency table, you put the data into list 1 and the frequency into list 2, and then you did your one variable stats, you're going to do the same thing. Except now, instead of having that second list be frequency, it's going to be relative frequency, which is the same thing as your probability. We also calculate standard deviation in our calculator the same way. You put in your two lists. List 1 is your data values. List 2 is the probability. Calculate your one variable statistics, and the standard deviation you get for a population is the standard deviation for your probability distribution function. Now, what the law of large numbers tells us, we can look at it in two different ways. A population has a true mean, a true parameter that is the mean of whatever it is you're looking at for all members of the population. Your sample, as it gets bigger and bigger, has a mean that gets closer and closer to the true population mean. The statistic, the mean for the sample, gets closer and closer to the true population mean as your sample size gets bigger and bigger and bigger and bigger, really big. Another way you could look at it is that if you have a probability distribution function, you will have theoretical probabilities for each value, and you'll have a theoretical expected value. The more trials you do, the closer the expected value for your samples gets, the number of trials you conduct, gets closer and closer to the expected value you would get theoretically. So here we have an experiment which is rolling a six-sided die. Now if we roll a six-sided die and record the roll, then our random variable, capital X, is going to be the roll of that six-sided die. The values that little x can take on, the sample space, the possible results of this experiment are the rolls, 1, 2, 3, 4, 5, and 6. If we construct a probability distribution table, remember we're going to put our x and our p of x. Now our book also puts a third column. That's not part of the regular probability distribution table, but it's important if we're going to calculate our expected value more by hand rather than putting our data into the lists and letting the calculator do it. So our possible values for x, 1, 2, 3, 4, 5, 6. These are all equally likely outcomes. So the probability that x equals 1, well, there's one way to get that outcome out of 6 possible outcomes. Probability that x equals 2, well, there's one way to get that outcome out of the 6 possible outcomes, and so on. Probability x is 3 is 1/6, probability of a 4 is 1/6, probability of a 5 is 1/6, the probability of a 6 is 1/6. Now, These are the two columns that make up our probability distribution table. And we know that if we add up the sums of these probabilities, we're going to get a 1 for this to be a probability distribution function. That's because you either get a 1, a 2, a 3, a 4, a 5, or a 6. You are guaranteed to get one of those. It is certain you will get one of those results. So the probability of those outcomes has to sum to 1. Now, the way our textbook likes to find the expected value is that for each one of these outcomes, we take that outcome and multiply it by its probability. Take the outcome and multiply it by its probability. What fraction of the time does that outcome occur? And when we do this, we get, it's kind of like a weighted average. So 1/6, 2/6, 3/6, 4/6, 5/6, and 6/6. When we add up this column, this gives us our expected value for this probability distribution function. We wind up with 21/6 or 3.5. So the expected value for the dice roll, and we call that mu, the same symbol we use for a mean, is 3.5. This will be X bar on your TI. Now, I'm going to encourage you to use your calculator to calculate this. Unfortunately, I need to talk to my IT guy to get an emulator put back on my computer so I can show you the steps. In the meantime, I'm going to put a link for a video that shows you how to use your calculator to calculate the mean or expected value, means the same thing, and standard deviation. But you would follow the same steps that you did in I think it was chapter 2 for entering data into your lists. If you recall, we enter this into L1, this into L2. We calculate our one variable statistics using this as our data and this as our frequency. So you're just going to do the same thing you did back then. So what does this tell us? This tells us that on average, for lots and lots of rolls, the average roll is 3.5. If we did this a whole bunch of times, added up all our rolls, and took the average, we would get 3.5. What doesn't this tell us? What doesn't this tell us? This tells us absolutely nothing. This doesn't tell us anything about the short term. It tells us nothing about what to expect if we only have a few rolls. You can't think that, oh, I rolled a bunch of 1s in a row, I've got to get a 6 to get my average up. It doesn't tell us anything about the short term. It doesn't tell us anything about a single roll. And it does not tell us to ever don't ever expect a roll of 3.5. You're rolling dice. There's no side with a 3.5 on it. So expected value is your average over the long term. It doesn't tell you anything about the short term, about any given roll, or that you should ever expect to get that exact value. That is an average. So here we are looking again at that probability distribution table for the number of times per week a newborn's crying wakes its mom after midnight. So we are going to do the expected value. I'm going to show you how to do it by hand. I encourage you to use your calculator. If you don't remember how, watch the video link that I post from YouTube on how to do that. And compare your work to mine. Make sure you get the same answer. So I'm going to do it by hand using this third column. We take the the data value times the probability of getting that value. Use an X for times because I have decimals. So that's a 0. 1 times 0.22 is 0.22. 2 times 0.46 is 0.92. 3 times 0.18 is 0.54. Oh, don't lose my decimal point. 4 times 0.08 is 0.32. And last but not least, 5 times being woken up occurs 2% of the time, and that's a 0.10. Now, if we add all these values up, we are going to wind up getting a 2.10. Again, use your calculator. Don't have to do it the long way. So the expected value of the number of times a newborn baby's crying wakes its mother after midnight is 2.10 times. Make sure you use your units. Even if you don't have to write a complete sentence, you do have to write your units. So this does not tell us to expect mom to be woken up 2.1 times on a given night or in a given week. Doesn't work that way. It tells you on average, bunches of moms, bunches of weeks, we add up how many times mom gets woken up divided by the number of weeks. 2.1 times is what we should get for an average. Now our standard deviation, again, you're going to use your calculator, and we're going to use this symbol. We're going to get sigma. And our standard deviation is going to be about 1.24. What does that mean? That is also 1.24 times. That's how spread out our data is. 2.1 is our expected value with a spread of sigma of 1.24 times. We want to know, is it unusual for baby to wake up mom after midnight? Well, never to wake up mom crying after midnight. Now remember, unusual means that it is more than 2 standard deviations from the mean. More than 2 standard deviations from the mean. So lower than mu minus 2 standard deviations or higher than mu plus 2 standard deviations. Oh, my mu looks like a W. Let me fix that. Okay. Mu, not W. So, for mom to never wake baby up, well, let's take that mean. Ooh, I should probably put the symbol for our mean right there. Mu. Remember, that's X bar on the calculator. So, mu, we already know we want to take mu. What is mu? Mu is 2.10 minus 2 times 1.24. Oh, it's not 1.24. It's 1.024. Lost a 0. And that makes a big difference, 1.024. So when I do that calculation, I wind up getting 0.052. So 0.052 and lower is unusual. .02, or I'm sorry, 0.052 and lower times is unusual. Because 0 is less than 0.052, never is unusual. Because it's more than 2 standard deviations away from the mean. Is it unusual for a newborn to wake its mother 4 times per week with crying? Well, is it unusual for a newborn to wake mother 4 times per week with crying? Well, that's bigger than the mean, so is it too much bigger? Mu plus 2 standard deviations is 2.10 plus 2 times 1.024. If you do that math, you're going to wind up getting 4.148, and higher is unusual. 4.148 and higher is unusual. 4 is not 4.18 or higher, so 4 times is not unusual. Oh, that's spelled wrong. Not unusual. Oh, no, I guess that is right. Okay. It's not unusual for mom to be woken up 4 times per week because that is less than 2 standard deviations above the mean. So here, I have a more exciting problem. Took this out of another stats book, and it was a real life problem, an actual situation that occurred, accusations of not choosing juries fairly. So here we have the probability distribution for the number of Mexican Americans among 12 randomly selected jurors in Hidalgo County, Texas. Here we have a theoretical probability distribution based on the assumption that jurors are randomly selected from a population in which 80% of the eligible jurors are Mexican American. So here, our random variable, X, is the number of Mexican American jurors or Mexican Americans selected for the jury. So on that jury, you can have 0 Mexican Americans, 1 Mexican American, 2, all the way up through 12. So here in our table, we have the number of Mexican Americans selected and the probability of that number occurring. The number of Mexican Americans and then the probability of getting that number on the jury based on a theoretical probability distribution. Now 0 plus, that just means that our number is so close to 0. This means that this is not 0, but very close. The probability, this got shifted somehow, so 0, 0, 0, 0, 4, 5. The probability of getting exactly 7 Mexican American jurors on a jury is 0.053. Just want to make sure I clearly see which goes with which. So here we have a histogram showing these values and the probability of them occurring. So here on the x-axis, we have the number of Mexican American jurors. And here on the y-axis, we have the probability of that number of jurors. So here, the probability of getting 10 jurors is, oh, look at that, somewhere between 0.25 and 0.3. Somewhere between 0.25 and 0.3. So we want to find the expected value for the number of jurors in a jury and answer with correct units. Again, use your calculator. I'm going to give you the answer. That expected value is about 9.598. So we expect about 9.6 Mexican American jurors on a jury on average. No single jury is going to have 9.6 Mexican Americans. Mexican American jurors on average. Again, tells us nothing about a given jury, only the long-term average. Standard deviation, again, use your calculator. And that's going to be about 1.39. And again, our units, Mexican American jurors. That tells you how spread out that data is. Not all that spread out, actually. It tells you how spread out we expect that data to be, assuming that juries are picked fairly and the population is 80% Mexican American. Is it unusual to have a jury with only 6 Mexican Americans? So 6 Mexican Americans, what is that probability? Well, right here. That probability, the probability that x equals 6, is 0.016. Another way, another way to figure that out is to know that 5% is unusual. But that's not what I wanted to do. What I wanted to do was I wanted to use the standard deviation again. So sorry about that. We'll do the other way in the next section. Got ahead of myself. So here what we want to do is we want to look at our mean minus 2 standard deviations. So 9.6 minus 2 times 1.39. And if we do that, we're going to get about 6.8. 6.8 and lower is unusual. So, is having only 6 Mexican Americans on a jury unusual? 6 is unusual because it is fewer than 6.8. Alrighty. That was section 4.2. Again, I am also going to post a link on how to find those expected values and standard deviations, or just do exactly the same thing you did in chapter 2 to find mean and standard deviation. 4.3 coming up.